Hello everyone, thank you for joining today's webinar on the zero prototyping approach in the development of induction heating equipment. I am Sumit Singh, an electric motor expert at EMWorks. EMWorks is a leading provider of electromagnetic simulation software for electrical and electronic designs from DC to millimeter wave frequencies. Our products are embedded in the most popular CAD platforms, namely SolidWorks and Inventor. They cover a wide range of applications ranging from electric motors, generators, transformers, and power electronics at the low frequency end of the spectrum to antennas and various wireless circuits and components at the high frequency end of the electromagnetic spectrum. I request all the participants to please feel free to ask their questions using the chat box option, and we will address all the questions at the end of the presentation. Let's have a look at our agenda for today. We will start with a quick overview of induction heating, the main principle, advantages and its applications. Then we will move to the well-specified application of induction heating, which is the induction hardening process for material heat treatment, in which we are going to discuss the main design and simulation challenges of this process. And we will cover the main EMS capabilities that will be used for such heating process. Then we will move to a live demonstration of the EMS interface inside SolidWorks. Later, using simulation with daily analysis of induction hardening, the process of sphere gear will be done. We will study the impact of some processing factors on the gear temperature, and we will try to estimate the generated electromagnetic and thermal stresses. And finally, a conclusion. As you know, induction heating is one of the cleanest, most efficient, and most precise contactless store for material heating, and it is particularly useful where highly repetitive operations of heatings are performed, especially for industrial processing. Simply saying, when applying an alternating current inside the coil, a time-varying magnetic field is generated. Now, when exposing a conductor material to this alternating field, and induced eddy currents are created inside it, resulting in high resistive losses, which will heat the material according to the Joule laws. When using higher frequency, AC currents tends to avoid traveling through the center of the solid conductor, which is called the skin effect. It is then circulating in a thin layer towards the surface of the heated workpiece. In turn, it leads to increased resistance of the conductor, ultimately resulting in a greatly increased surface heat. This process is based on two tightly coupled phenomena, electromagnetic and heat transfer, with their fundamental Maxwell and Ohm's equation, which is the main advantages of induction heating. It is an energy-saving heating process controllable by many factors like the heating time, the current supply, the usage frequency, and the material to be heated. It allows rapid and precise localized heating, and it is essentially used for highly repetitive heating, which makes it easy to integrate into production lines due to its efficiency as a fast, clean, and secure technology. Now, let's have a look at some of the main induction heating applications for the industrial domain. Induction heating is essential for heating processing, where highly repetitive operation of heatings are performed, especially for material heat processing like hardening and tempering, melting, casting, brazing, and even preheating for welding. It is also used for non-destructive testing operations by thermography for crack detection, or to heat the thermoforming modes for dominating domain. We have the famous induction heating and boilers for now medical and healthcare. Domain induction heating is essential for hardening surgical blades and brazing steel for auto-sensing parts on the right. As you can see, some of the applications of induction heating that were investigated using EMS for SolidWorks. We have induction heating molds, the non-destructive testing for crack detection by thermography. We have the induction heating cook, or the preheating for turbine blades and for hardening steel tubes, etc. Now, as an engineer or designer, before going to the experimental heating steps, several factors can be involved in the design, modeling, and simulation steps of induction heating. Those factors strongly affect the desired results, like the temperatures, the heat profile, the hardening rate, and even the material state. And those factors can be related to the design, like the inductor or the inductor position according to the heated part, or could be directly related to the main process parameters, like the heating times, the use of frequency and skin penetration depth, the usage heating materials, the excitation power supply, speed of the rotating part for progressive hardening, or to regenerate electromagnetic and thermal stresses. All those factors could be covered using EMS, but for our today's webinar, we are going to focus on the highlighted aspects in which multi-configurations feature is used to vary the conductor design, as it is an important factor that defines the heating profile and distribution. The heat transfer analysis will be performed using a transient thermal solver to model the time-varying heating operation of this sphere gear, and later to optimize your hardening process in terms of optimal frequency and hardness penetration depth. A parametric analysis coupled with thermal inside EMS will be used to reduce the simulation time and compare the effect of those factors on your design within the same study. The accuracy of the computed temperature could be also improved with the use of temperature-dependent materials to converge to the realistic co-working condition of the hardening process. And finally, heat and mechanical stress could be studied to estimate the mechanical deformation caused by thermal stresses and generated forces inside both the coil and the hardening component. We have also performed a high level of accuracy validation against lab measurements using our tool EMS, which is developed by EMWorks. So for example, you can see a 3D CAD design of the studied model, which has some coil channel and core and cavity plate. So you can look at its temperature distribution and very interesting graph, which we have a temperature variation versus time for both experimental and the EMS software results. And you can see the results are on par, and also if there is like a small deviation from the experimental results, but at the end the cost of the simulation is always cheaper than having the cost of creating multiple prototypes. And that's what the advantage of having a virtual prototype platform, where you can approach to a zero prototypes. Moving on, next we have also simulated a 3D model of mold plate with both 3D and 2D coils, and also you can see the experimental data and these results generated by the EMS softwares are having almost a close match. And we also performed for 3D coils as well as for the 2D coils, and you can see the results are very good enough. Next we have magnetic pulse welding system, where current waveform was a damping nature of current waveform was excited to the coils, and you can see the magnetic flux of the field shaper from the EMS software and the reference results, which is the experimental results, are having a good close match. Well, for today's webinar, we will inspect induction hardening, since it is one of the main industrial applications for surface material treatment. Some mechanical parts which are frequently exposed to continual external stresses require hardening process to provide optimal performance and long expectancy life. So induction hardening allows an efficient way to thermally treat gear shafts, bearing tubes, pipes, etc. So induction is the perfect solution for many hardening requirements, like the fast heating rate, uniform temperature, and easy heating control. This process is characterized by a fast heating rate with a short circle time. It can be applied to external internal surfaces, and it allows a well-selective localized source hardening by creating higher residual local stresses without affecting the rest of the parts. It helps to get easy controlled heating where the heated parts have higher fatigue strength without any limitation of hardening profile or workspace geometry. Now let's move on to the simulation part. AC module from EMS is used for the frequency domain. As already mentioned, the heating component is a speed gear designed with 9 teeth modules equal to 4 mm. The required hardness and cost are very important factors to consider when selecting materials for the hardening gears. The used material for our simulation is stainless steel, which is SUS 304. When hardening is performed, uniform heating is required for the hardening penetration depth. So trying to select the optimal coil design to get a good heating profile is very important. SolidWorks multi-configuration features coupled with EMS simulation is then the perfect solution for it. 3 different coil designs were performed to analyze the heating profile of the steady gear during this process. Now let's check together how will be the temperature distribution for each design. Moving ahead, for this first coil design, which is made up of 1 ton conductor with the gap separating the entry and exit ports. If we consider static hardening when both the inductor and the gear are fixed, the 5 seconds of heating for a frequency of 30 kHz are enough to heat gear to the desired temperature mentioned in the previous slide. So because of it, we obtained the following induced eddy current density distribution, which looks in a form unacceptable, where the maximum is concentrated in the root regions between the root region of each. But what about the temperature? As you can see from the following temperature distribution, it is not symmetrically distributed essentially around the teeth region, even if the 0 pole temperature rates are attained. So after being quenched, hardening won't be any form too. Then this is not a good enough. So moving on to next design. If we try to use a closed coil design, because now we know the problem is the gap between the entry and exit parts. Let us see if the heat profiles will be adjusted or not. With this design, we will consider the same heating and excitation conditions are the first one. Our current now looks much more symmetric. The same things for the temperature. So it follows the turn of the profile and achieves the required heating rates with an average of 800 degrees Celsius for the desired depth. So this design solved the symmetry issues, even if the maximum where the red zone doesn't cover all teeth contour, but it will be improved later when playing with the material properties. Now, what about the high excitation current? Could we solve this with another coil design? Let us see. With the third inductor geometry now, we have a multi-target score for the same heating time and with the same frequency. With this design, we could use only half of the excitation current to achieve the same current and temperature as the previous design. The current results looks acceptable and symmetric, but the temperature is not the case. As you can see, a big difference in temperature values between the teeth, and the uniform heat profile is lost with this design. Even if we profit from lower excitation currents, so for our starting hardening, it will be better to use the second closed coil design for the rest of our investigation. And now let us see how the variation of the peak could help to select the optimal one that improves the heating profile and rates. So parametric analysis coupled with thermal is performed to select the optimal frequency and its impact on the skin depth and eddy losses. Now we are interested in the supply frequency, which will vary between two values, minimum of 25 kHz and a maximum of 100 kHz. And automatically it affects the skin depth according to skin depth expression. So when the frequency gets higher, more fine mesh elements across the skin depths are needed, which could be easily controlled by mesh refinement parameterization for the skin depth variable, as it is an automated process in EMS. So because of this frequency swipe, we have the variation versus frequency of skin depth figure as well as the attained eddy losses, which increased proportionally to it. The plot shows the loss density distribution for the first and the final frequency for 25 kHz and 100 kHz, from which we can easily note the localized losses within the zero penetration depth. Now, if you want to have a close idea about precise number of the last densities, then you can use the 2D plot of this spatial variation between 2 points A and B, and one tool which was selected from the gear based circle and plotted versus frequency. So we have now in the figure the interpolation along the AB line for the different scenarios. We have a symmetric distribution for which we can easily notice the variation of skin depth via the increase of losses of density, and at the right and left regions both, which define the hardening tooth contour. Now, what about the temperature results? So let us have a look at it, since it will define the hardening rate. For the following temperature results at the first and the final usage frequency, we can conclude that lower frequencies are used to heat the gear routine, and higher frequencies are essentially used to heat the top heat surfaces and at higher temperature values. So we saw the impact of frequency sweep on the losses and skin depths. Now, how to select the optimal frequency according to temperature? If you remember from the steel phase diagram that we showed in the previous slide, steel should be heated to a temperature between 750 and 950 degrees Celsius. So for our case, and based on the second plot of the variation of temperature versus frequency, we can confirm that the heat for our heated gear design frequency would be around 30 kHz. Now let's move to the effect of material property. How could it be improved the heating profile? So to get as close as possible to the concrete hardening conditions and to accurately predict the achieved temperature magnitude and profile, EMS allows using a non-linear temperature and bonding material properties for electromagnetic, thermal and mechanical properties, with an internal two-way solving between the electromagnetic and thermal solver within the same analysis and inside the same interface. For our case, we have used the temperature depending thermal conductivity of the heated gear, and we found that the heating profile of the heated gear is more accurate and realistic, as you can see from the figure, compared to the case of constant thermal conductivity. Now we got a well uniform heating profile from the same obtained temperature distribution. We selected 3 points T1, T2 and T3, which are located respectively at the inner diameter of the gear hole, at the gear root and the two top surfaces. The plot is showing the temperature variation between T1 and T2 and between T1 and T3 for the space between T2 and T3, which defines the working depth. The variation of temperature is very small, between 820 degrees Celsius and 870 degrees Celsius, so it is well to define the required temperature rates for the hardened profile. Now, what about the generated electromagnetic and thermal stresses? High current may result in higher temperature stresses and Lorentz force in both gear and inductor parts, which lead to structural deformation. EMS can be used to analyze this behavior. In addition to temperature, EMS computes Lorentz force in conductors with current, and both, I mean the thermal response and the electromagnetic, including the Lorentz force and magnetic forces. So for the coil, a high circulating current generates Lorentz force, which could be computed and visualized by force distribution in the figure on the left when it is fixed from the top and the bottom faces. The coil is performed under the effect of those forces, so EMS allows for computation and visualizes the formation, which is symmetrically distributed across the coil and achieves a maximum value of 7 nanometers. Same thing for the heated gear. The force density distribution is shown in the figure. Maximum forces are following the eddy current profile, which is concentrated at the gear rotations. Now when fixed from the central hole, the maximum gear deflections are localized across the teeth parts. Overall, under only the effect of electromagnetic forces, attained stresses are relatively tolerable and acceptable. Now, when added to the electromagnetic effect, thermal stress is allowed to obtain the forum or results. So after solving the thermal part, thermal loads, which are part of temperatures, are fed to the structural solver to compute the thermal stresses sequentially and then predict the produced mechanical deformation. The attained displacement is significant compared to the electromagnetic effect alone, which confirm the strong effect of temperature on the gear structure after being extremely heated. Now let's go through a quick exploration of the EMS interface inside SolidWorks and check the main features that we have used today. As you can see, EMS is fully integrated inside SolidWorks, and they share the same interface where the user can work on both CAD design and EM simulation with multi-physics analysis. Here are the added tab of EMS. Inside it we have many study types for magnetic and electrical analysis. We have the magnetostatic, AC magnetic for frequency domain, and transient magnetic for time domain. And for electrical studies, we have electrostatic, AC electric, and DC conduction. As you can see, all study types could be coupled to parameterization. Many types of coupling could be added to each study type according to the user requirements. Thermal with both steady state and transient, structural, motion, and circuit coupling. For SolidWorks multi-configuration, you can see how to switch between configurations with only a few clicks to activate and deactivate geometrical configurations with different coil designs, and synchronously the corresponding studies to do the same. Now, for each study, the user must define sequentially the material from a material library on the right with detailed material properties, whether it's electric, magnetic, thermal, and mechanical, or he can simply customize his own material or load it from an external file. Then electromagnetic, thermal, and structural boundary conditions can be set, and also the mesh with mesh control can be set. And finally, the results as shown here, such as magnetic flux density, magnetic field intensity, electric field, pore density, losses density, its flux, voltage and current, and many more. Now to summarize today's webinar, different aspects of an induction heating applications were addressed by using the EMWorks tool. The different design issue posed by the single shot and action hardening process in the static case were analyzed. The integration inside SolidWorks platform allows more flexibility in the design and optimization of the induction coil and heated piece. Through this webinar, we try to show you how EMS is allowed to select the optimal cradle design for static induction hardness and to select the optimal frequency according to the desired penetration depth. Also, the effect of nonlinear temperature depending on material properties on the heated profile was investigated. And finally, we tried to estimate the generated of the coil and gear entering electromagnetic and thermal stresses. A high level of accuracy against lab measurement was also achieved and was shown by using the EMWorks solutions. And as you know, both 2D and 3D electromagnetic analysis are used to maximize productivity and reduce the time to market. Therefore, a single platform of EM multiphysics simulation is provided to create a complete CAD embedded simulation environment to replace the prototype phase. Thank you so much for attending today's webinar. Please visit our website www.emworks.com, and now the session is open for question and answer. Again, I would like to thank all the attendees for joining our webinar today. So let's start with the first question. So we have, what are the limitations of induction hardening? Well, if I would say, like, since as we have seen in our webinar that to heat any particular spare gear, you need to have a coil around it. So the first limitation which comes to my mind is we require an induction coil which can relate to the part's geometry. So you need to have a custom built coil which can cover up, because you have seen even if you have a gap between the coils, it affects the temperature distribution. And so it's very important to have a round coil which we investigated for the further analysis. And obviously those coils are very limited to your part of a geometry and the part which you are going to induction hardening. So that could be one of the limitations. Every time you need to come up with a custom build so that you have a better efficiency. Next, I can say is that it's not suitable for all the type of materials. So this method is very limited to this few materials, like such few like carbon steels and some grade of materials which can be heat treated, because like you have seen that it creates a rapid heating and quenching of the material. So it might also lead to create a hotspots which can further creates a cracking into your parts of the material. So since we are heating it very rapidly, so it's not suitable. This method is not suitable for most of all the materials. And yes, these are the few options. What are the limitations of the induction hardening? Also, I would like to remind you, please visit our website and register for the upcoming interesting webinars. We have webinars applications ranging from low frequency to high frequency. And if you have missed any of our past webinars, then you can fill out the form for the webinar recording request, and our team will be glad to send you the recording. And also, if in case if you have any questions or doubts for us at the later stage, then you can always contact our team through the contact us option in the web portal, or you can approach us through our LinkedIn EMWork user group page. So we'll wait another 1 minute for any more questions if we have from our attendees. And we have one question that I would like to have a video. For sure, we will be sending you an email, even like the webinar recording request, and you can get the complete presentation video. Well, so thank you once again for all your queries, and see you in the next webinar. Thank you so much. And yeah, you're welcome. Yeah, thank you so much.